Okay, so hello everyone. Welcome to the problem solving sessions for Introduction to Automata Languages and Computation. So, in this week, we will look into um, yeah, we will look into different models, which is one is to DFA. We will define what this is. We will also look at automata with output. So these are called Mealy and Moore machines. So we will look at what these machines are. These are basically DFAs with output. And throughout this tutorials, you've been designing different DFAs and so on. And by now we know that for a single language, you can have multiple, in fact, lots and lots of DFAs which accept the same language. But of course, it would be of interest to know what is the minimum size DFA that recognizes the language. So, is there like a technique to technique to obtain the minimum sized automaton? So, we will look at an algorithm for obtaining minimum sized automaton. So we will define these models as and when we come across the questions. So let's start with the first question. Okay. So you're given the following automaton, and you want to tell what is the minimum number of states required by a DFA to recognize the language. So in particular, the DFA that is given has 6 states, but can we do with lesser states? So could you for example come up with a DFA with 4 states and still recognize the same language? So in the class we saw an algorithm for doing the same. So we will follow the steps. So what is the algorithm? The algorithm is that first you start with 2 sets only. One which is set of non-final states. Sorry. So in this case, the set of non-final states is Q0, Q3, and Q5. And the set of final states is Q1, Q2, Q4. Okay, so now what we do is for every so this is this just one state for us now. Then we will see on 0 where does this go, and on 1 where does this go. So if let's say for example on 0 Q5 on 0 maybe goes to Q3, so it sort of stays here. But if Q3 for example on 0 goes to a state here, say let's say Q2, then we say that the states are not equivalent. So in that case we will split our set. So let's do it for this example so that becomes clear. Okay, so let's look at this set of non-final states, and let's see where does Q0 go on 0. So Q0 on 0 goes to Q3, so it stays here. Q3 on 0 goes to Q0, so it again stays here. Q5 on 0 goes to Q5 only. So in each case we stay here. So Q0 is not able to distinguish. 0 is not able to distinguish the states. So let's try for 1. So Q0 on 1 goes to Q1, which is here. Q3 on 1 goes to Q4, which is again here, and Q5 on 1 however goes to Q5, which is here. So now we have we're sort of seeing that there is a difference between the behavior of the states Q0 and Q3 and the state Q5 on reading input 1. So in particular Q5 sort of stays in this set of non-final states, whereas Q0 and Q3 go to the final states. So let's break this set as follows. So you have Q0, Q3, then you have Q5, then you have Q1, Q2, Q4. Okay. Yeah. Now let's check whether we'll repeat the same steps, but for the final states now. So let's see where Q1 goes on reading a 0. So Q1 on reading a 0 goes to Q2. Then Q2 on reading a 0 stays at Q2, and Q4 on reading a 0 stays at Q2. All of them are actually in the same set Q1, Q2, Q4. So again, we are not able to distinguish. So let's see what happens when you read 1. Okay, so now when you see a 1, Q1 goes to Q5, Q2 goes to Q5. Hi. Okay, and Q4 goes to Q5. Hi, so am I audible for you?
Yes.
Okay, so what we're trying to do is we're trying to do minimization of this automaton. So you're given this automaton with 6 states. You want to see whether there is an automaton with less number of states which still recognizes the same language. So how do we do that? This is called minimization algorithm. So initially you take all the non-final states. So in this case, the non-final states are Q0, Q3 and Q5. And the other set is that of final states. Then imagine that you have only 2 states now. One is this and one is this, and we're going to split them based on the behavior. Okay, so for example, if you look at Q0 on 1 goes to a final state, which is here, and then Q3 also goes to a final state, which is here, but Q5 stays here, which is a non-final state. So Q5 somehow has a different behavior than Q0 and Q3. So that's why we have split this set into 2. So now we have 3 states. One is this Q0, Q3, one is Q5, and the other is this. Now we're doing the same thing with the set of final states. We're trying to see if they behave differently on transitions on 0 and 1. If they do, then we will split them again. So in this case, all of them on reading a 1 still go to Q5. So we are not going to split. But let's see what happens on 0. So if you read a 0 from Q1, then you go to Q2. If you see a 0 from Q2, then again you go to Q2. Yeah, and if you see a 0 from Q4, then again you go to Q2. So again, in this case, whether you read a 0 or you read a 1, it goes to the same state. So we can't continue the process further. So hence, this gives you the minimum automaton. So what does it look like? So let's draw the figure. So you have one state which is Q0, Q3. Then you have one state which is Q5, and the other which is Q1, Q2, Q4. Okay, so what should be the start state? Whichever state contains your Q0, because Q0 is the initial state in the given diagram. So the set which has Q0, which in this case is Q0, Q3, should be the start state. Now, how do we draw the transitions? So so from Q0 or Q3, if you see a 0, then you basically stay there. Can you tell me where should we draw the transition for 1?
Q1, Q2, Q4.
That's right. Then from Q5, Q5 you basically stay there on 0 and 1. Then from Q1, Q2 on 0 you stay here, and on 1 Yeah, on 1 you go to Q5. Yeah, and what should be the final state?
Q1, Q2, Q4.
That's right. So because all the final states of the previous DFA are here, this should be your final state. So, I mean, you can check in terms of language also later on that indeed both the DFAs recognize the same language. So in this case, we could basically get a DFA with 3 states. So yeah, so D is the answer. So let's look at another example.
Can you explain the working of minimization algorithm?
Okay, so so initially, basically, we don't know what all groups can be clubbed together. So you start the other way around. You only start with 2 states. One is a state which only consists of non-final states, and the other is a state which only consists of final states. Okay, then you check on all this, like there could be, let's say there is Q1, Q2, Q3 here. Then you check where does Q1 go on 0. So suppose Q1 on 0 stays here, but Q2 on 0 goes to, let's say, final state. In that case, what we will do is we will split this. So Q1 will sort of be some other state because its behavior is that it stays here. Then Q2 will become a state that goes here. But let's say Q3, for example, behaves same as Q1, then Q3 will be here and we will remove this state. Then you do the same with final states also. This will also get splitted and so on. So finally, when you can't split further, you get a DFA which is the minimum in that sense.
Okay.
Okay. So yeah, here you are given a DFA, and there are 4 statements that are written. You want to tell which are the correct statements. So I'll wait for a couple of minutes.
C.
Okay. So okay, so 2 is correct, that the language of this DFA that is given is okay. So let's write. So we're checking whether statement 2 is correct or not. So if you I mean, the only way to reach to Q3 is either you read a 0 or you read a 1 followed by 1 star, which is here, and then a 0. So either you come from here or you come via this. So that is what this is capturing. And yeah, then basically once you reach Q3, it's any number of zeros or ones. So that's nothing but
0 plus 1 star.
That's right. So that's nothing but 0 plus 1 star. And the rest is sort of redundant. Even if you don't write, it's still the same language. So yeah, this is correct, that the language accepted by this automaton is indeed this. Now let's look at 1.
So option 2 is incorrect or correct?
Correct. Yeah, it's correct. I mean, even if you have the 0 star, 1 star, it's sort of redundant. Because this is,
Okay.
yeah, I mean, because 0 plus 1 star, 0 star, 1 star is same as 0 plus 1 star. So it's the same basically. Okay.
So it will be 3 and 4. Option D. Or the false.
3 and 4. Yeah, that's right. That's right. So, yeah, the given, I mean, clearly we have drawn a DFA for this. I mean, so it's regular, and its complement will also be regular by closure properties. So L of A is regular, implies L of A complement is regular. So yeah, these two are correct. Now let's look at 3. Okay, so we want to see whether you can further minimize this DFA. So we'll do the same process. We start with two states, one with two set of states, one which is the non-final states and one which is the final state. Then we look at the behavior. So let's see what does Q1 do on 0. On 0, Q1 goes to Q3. And Q2 also goes to Q3. So both of them sort of go here. So we can't distinguish it based on that. Then let's see what happens on 1. On 1, Q1 goes to Q2 and Q2 goes to Q2 again. So both of them sort of stay here on 1. So we can't split this further. And there is no point of asking the question for this because there is only one state. You can't even split it further. So in one step itself, we saw that yeah, basically if you just start with these two states, so this is one state, this is the other state, and this is initial because Q1 was initial, and this would be final because Q3 here is the final state. And then what are the transitions? On 0, yeah, on 0 you go here, on 1 you stay, and on 0 1 you stay here. So this is basically the same language as what this was recognizing. This is 1 star 0 followed by 0 or 1 star. So yeah, so you can indeed minimize this DFA. You can make it a two-state DFA. So hence this the given diagram here is not minimum, so 3 is false. Is this okay?
Yes.
Okay. And fourth one, you can yeah, you can, I mean, you can observe that for example,
It will be at least one length string.
yeah,
0.
yeah,
One length string.
I mean, that would not be a counter example. A counter example would be a string of length 2.
It will be at least of 1 from Q1 to Q3.
Yeah, that is right. But if you say that something, I mean, the statement says that it accepts. So if you think of, or maybe I'll just write 0 0 0 1 1 0 1 1 and then all strings of length 3 and so on. So basically this is the set of all strings of length at least 2. So the claim is that this is a subset of the language of the automated. You agree with this?
Yes.
Okay, so if you want to show that this is not a subset, you want to show that there is an element here which is not here. There exists some x in L of A such that x is not in, if I call this S.
In fourth option, they are asking for the minimal length string, so we can directly write that it accepts minimal length string of length 1.
No, it is not saying that it doesn't accept strings of length 1. It is saying that every string of length 2 will be accepted.
Okay.
Okay, so yeah, I mean that is independent of whether it is accepting one length string or not. But here it says that every string of length 2 will be accepted whether one length string gets accepted or not. So to show that it is not correct, we will just give a string of length at least 2 which is not accepted.
Okay.
Okay, so in this case, that is here you basically go from Q1 to Q2 and just stay here. So I mean, a long string of ones would be a string which is of length at least 2, but it is not accepted.
1 plus basically.
1 plus, exactly.
Okay.
Okay. So, yeah, so for 4, the counter example would be 1 1 followed by 1 star. Okay. Okay, so I'll just write, if for those who are just going to look at the PDF, I'll just write that D is the correct answer. Okay, so yeah, this is a question about two DFAs. So maybe I'll first recall what are two DFAs. Okay. Okay. So I mean, let's try to recall what is a DFA to. DFA basically has a set of states like this. Then if you give me some string 0110 something, you basically start from here. You go on. I mean, just follow the path. Whatever the DFA tells you, you just keep on following the path. Ultimately, when you have read the entire string, wherever you are, if it is final, you accept. If it is not final, you reject. But you cannot ever like say that okay, I'll read like 0 first. I mean, okay, 0 first here, and then you can't say that okay, then I read 1. For the next one, you won't say that okay, I'll come. I mean, after reading the whole thing, you will never say that okay, I've read 0 1 1 1 0. Okay, and now I'm here. Now you won't say that okay, I'll start looking backward. Again, I'll read 1 from here or 0 from here, because by definition, DFA just reads the string once and then decides okay whether I want to accept or not based on the state that I landed in. But 2DFA is basically more flexible in the sense that it's a two-way DFA, meaning you can go to the left or you can go to the right. So let's see how that happens. So you can imagine that there is a long tape like this, and this is like a left end marker, and you have your string written on the tape. So let's say it is 101010, and then there is a right end marker which tells you that this is the end of your input. Okay, so at the beginning you're always here. Okay, then you go to the left, then you go to the right. So whenever you read a 1, you decide whether you want to so delta tells you if you are in some state and you see a 1, then you go to some state. So maybe q2. Okay, but additionally, what you're also going to do is you're going to tell where the tape should go, where the marker should go. So if you are here, then you're going to tell whether to go to the left or right. So you're also so maybe let's say we say that not just that you go to q2, but you move to the left, or maybe let's say right in this case. So what will it do? From here it will go here. Then let's say from q2 there is a transition which says that q2 on reading a 0, it goes to some q prime and goes to right again. Then you will make a transition to q prime and you will move this head to right, and it will keep on happening like this. So you're basically doing everything that a DFA does, but you're also moving your header on the tape either to the left or to the right. But then how do we decide whether when to accept? Because it could just keep on going to the left and right and never even accept. So for that, we have a special state which is called S. This is the accept state. And there is a special, okay, I'll call this T maybe. Okay, and there is a special state called R, which is the reject state. So what happens is, if ever while doing these transitions, if you ever reach T, even if you touch T, you're going to accept the string. And if you ever touch R, you're going to reject the string. Okay, so maybe let's take this example so that things become clear. So So yeah, here you are given a language which is set of all strings whose second right digit from uh, I mean strings like this which has one from the second position from the right, or like strings like this and so on would be in the language. Okay, so how do we make a 2 DFA for this? So the idea is very simple. You start at a state, then uh, yeah, you
Second digit will be 0, no? In the given that
second
example.
from the right. You're looking from the right, from here.
Okay. Okay.
Okay, so the idea is that uh, the 2 DFA, because it has power of going to the left also. In case of DFA, you couldn't have done that. You can't say that I'll first go all the way to the end, then I will come back and see whether the second position from the left was 1 or not. Because DFA doesn't allow you to read back. Once you are done reading the last bit, you are done. You have to decide whether to accept or not. But 2DFA has this power that it can read the input, like sweep in left and right, and read as many times as until you see this one of these two accept or reject state. So that's what we're going to exploit. Okay, what we will do is we will read the input all the way to the end, then come one step back, see whether it is a 1. If it is a 1, then accept. So informally read the input all the way to the end, then move one step left, if it is 1, then accept, otherwise reject. So this is the informal idea. We will just draw the automaton for the same. So yeah, so okay, first thing is that your your head is going to be at the left hand marker, so anyway you have to move to the right. That is the first step. So what you do is from Q0, if you from this left hand marker, you okay, maybe for simplicity I'll just assume that your head is here. Okay, so now if you yeah, if you see a 0 or 1, yeah, if you see a 0, you go to the right, because that's what we want to do. No matter what you see, you just want to keep on moving right until you see the right hand marker, which tells you that you have reached the end of the input. So if you see a 0, you just keep moving to the right, and if you see a 1, again you keep moving to the right. So yeah, so that's what we do. Now when you reach this once you have read all the inputs and finally you reach this right hand marker, then on reading this right hand marker, you just move one step to the left so that you are here. Okay, so that is your state Q1. And is this the bit that we want to look at? We basically, this is the last bit of the string. We want to look at the second last bit of the string, so we should move one more step to the left. So from Q1, no matter what you see, whether you see a 0 or you see a 1, sorry, I just to be consistent, I write, whether you see a 0 or you see a 1, you should just go to the left. Okay, now we are at a, yeah, we are basically here. What we did is we started from this place, we just kept on moving blindly, we kept on moving until we reached the end of the input. Then we just moved one place to the right, so to the left, so that we are at the last bit of the input. Then we moved one more step to the left, so that now we are reading second last bit of,
From Q1 to Q2, it will be left or right? Between Q1 to Q2.
yeah, it should be left, because at Q1 you are here basically, you are here.
But transition is from Q1 to Q2. That is in right direction. No?
This left and right is not about the direction, it has nothing to do with the states, it is on about the tape. So your input is written on the tape here. Okay,
Okay.
Okay, and there is a header that tells you what input you are reading. So this left and right is about the position of this header. So okay, 1 second. Okay, so the header is basically going to tell you what to read. So initially you were here, let's say. So what this right tells you is that you read the next bit. Then again you are at Q0. Again it says read the next bit. Again it says all the way because of this. Okay,
Okay, and between Q0 to Q1, what you have written on the edge? That is R or what?
that is left. Okay, this is the right hand marker. Okay, here this thing is a right hand marker. It tells you that you have reached the end of the input.
Okay,
Okay, so that means I have read the entire input. Now what I should do is I should go back here, 2 steps here, so that I can read the second last bit from the right.
okay,
Okay, so this left basically tells you, oh, now you are here. Now you should go here.
okay,
Okay, and that is not the bit we want to read. We want to read the second last bit. This is the last bit. So again, we should go one more step to the left. So that's why here we have a left. Okay,
okay, understood.
okay. So yeah, these right and left transitions are about the tape. It is independent of what state you are in. Okay.
And it is a type of DFA only, right?
Yeah, it is a DFA because the transitions are deterministic. Like from one state, you cannot go to different lot of different states. There is a fixed transition. On seeing a zero, you only go to Q2. But there are like variants of this. I think I'll talk about it at the end of this example. So yeah, so when you reach at Q2, you are basically looking at this bit here, and that's what we want to check. So if you see a 1 at this point, you're going to accept it. So this is the special accepting state, which is called T. But if you see a 0, then you should reject.
Okay, and on Q naught, you have written 0 and 1 both on Q naught only. So it is a DFA or NFA then?
It
Like
is a
for
D.
both inputs, the transition is only till on the same state, no?
Yeah, that is I mean that is okay with the definition of DFA, because it just says that if you are at some state and you read some symbol, then you should just tell me where to go. So it
Okay,
can be that Q0 on 0 goes to Q0 only, and Q0 on 1 also goes to Q0. It doesn't violate the definition of transition function.
okay,
Okay. And then like it doesn't matter like whether you go to the left or right, just for the sake of it, I'm keeping it left. And then no matter what you see, you just yeah. Yeah, I mean, by definition, once you reach the accepts it, you are going to accept it. And if you reach the rejects it, you are going to reject it. There is no way that you can, from a reject state, you can ever go to accept state and so on. So, I mean, all of this is just sort of sanitary check. It's just to make sure that the DFA is well defined. So, okay, yeah. So, one thing is that um, you can like similarly you can use the same idea and you can define NFAs. You can generalize NFAs to two NFAs. Okay, so that and all is also, I mean, it is also a very well studied model, but it's not a part of this course, so we will not be looking into it. But one interesting fact about this is that we saw DFAs, then we saw like a slightly more powerful uh, thing which is NFA, but it turned out that both actually are same equally powerful, because they for every NFA you can come up with an equivalent DFA. Now we are looking at this 2 DFA, which looks like it has more power because it can read, come back and read and so on. It can go to the left and right and keep on doing that. But it also turns out that they are also equivalent. So all of these are basically equivalent. But the proof of that is not a part of this course, but just just to let you know, yeah, this is there. But why do we study the 2DFA model is because sometimes it's easy to to design a 2DFA than a DFA, because now you have seen lots of examples. So this language L is like easy for you because you can obviously design a DFA for it. But had you not seen it before, the most natural thought for you would have been, oh, you want to check whether the second last digit from the right is 1 or not. The obvious thing for you would be, okay, just go all the way to the end, then come back and see whether the second last digit is right or not. So it's kind of more intuitive that way. So okay, so we will see one more example for about the 2DFAs. So here you want to design a 2DFA for languages, for the language which is a set of all strings, such that the number of A's is a multiple of 3 and the number of B's is a multiple of 2. So just as an example, A, or let's say A, B, this would be in the language, but for example, this would not be. So I'll wait for some time for you to think about it, and you will be tempted to come up with a DFA because that's what we have been doing so far. But if you want to design a 2DFA, just think of the most obvious, natural sort of thing that you would do to come up with the language. Like in the previous case, the most obvious thing was that you go to the left and come to the right. So similarly, if you think of the most obvious way, um, you'll be easily able to come up with a 2DFA. So I'll wait for you to try.
Ma'am, can you explain this one? This.
The designing of the DFA.
Uh,
Okay, sure. Okay. So, like intuitively, what we want to do is there are two checks. One is that we want to check whether number of A's is a multiple of 3, and we want to check whether number of B's is a multiple of 2. Okay, so it would be very easy if you basically you have given me some string here, something like this. There is a long string and then there is a and then there is a right-hand marker. So this is basically our input. Okay, so what is the most natural thing? Natural thing is that I'll start here, okay, and then I'll somehow keep a count of number of A's. So here I'll just keep on moving to the right. If I see B's, I will ignore. If I see A's, I will maintain a count whether it is a multiple of 3 or not, and I will keep on moving right. At the end, when I reach here, so ignore B's and count number of A's. Okay, so and keep moving right. Okay, once we have made one full pass, we will reach the end marker. Okay, so at the end, okay, what will we check? Because we only counted the number of A's, we will just check if number of A's is a multiple of 3. If yes, if no, then you anyway reject, because it is already violating the condition. We want it to be multiple of A's as well as multiple of B. If yes, then you continue on the third step. Now what you want to do is, in the whole thing we checked whether the number of A's is a multiple of 3. Now we want to check whether the number of B's is a multiple of 2. So what we will do, we are here, we will we will move all the way back to the front of the input, and on the way we will count the number of B's. So keep moving right. Sorry. To the left and count number of B's. And by that we mean that if you anyway see 0, then you just and if you see A's, then ignore. Okay, once you've reached all the way at the left end marker, simply check whether the number of B's is a multiple of 2 or not. Check if the number of B's is a multiple of 2. If yes, then we are going to accept. If no, then we are going to reject. So just to take an example, can you give me a string to write on the tape?
AAB, ABA.
Okay. So we will start from here. Okay, and we are going to count the number of A's. So at this point, the number of A's is 1. Then you move to the right. Number of A's is 2. Then you move to the right. You see a B. We are going to ignore. So the current count is 2. This is going to be ignored. Then you move to the right. Number of A's is now 3. Then you move to the right. You see a B, ignore it. Move to the right. Number of A's is 4. And then you move to the right and you reach this end marker. It tells you that okay, you have finished reading the input. Okay, at this point, so all this thing that we did here, this was step 1. We basically ignored all the B's, counted the A's, and we kept on moving to the right. So now we have reached here. Now step 2 says that at this point you're going to check what is the number of A's you saw. Is it a multiple of 3? So in this case you saw 4 A's. So it is not a multiple of 3. So we're going to reject. That's what it says. If it's not a multiple of 3, then you reject. But let's say my example, I'm slightly modifying your example. Let's say this A was not there and this was the end of input. Okay, then, or maybe this is the end of input. Then in this case, the step 3 will come into picture. So step 3 says that okay, now you are here and we know the number of A's is a multiple of 3. Now we want to see whether the number of B's is also a multiple of 3. So what do? We just keep moving backward. So you are here, you go to the left and count the number of B's. So here number of B's is 1. Then you go to the left, you see an A, just ignore it. Then you see a B again, so the count is 2. Move to the left, you see an A, ignore, you see an A, ignore, and move to the left again. Now this end marker tells you that you have again finished reading the input. At this point, we will go to step 4. Number of B's we saw here is 2. And then at step 4, you just see whether it is a multiple of 2. In this case, it is, so we will accept it. If it were not, then we would have rejected. So is that informal idea clear?
Yes.
Okay, so now we will draw the automaton for that. Okay, so you start at some state Q0, and what we want to do is, again I'm assuming that your input is here and your head is here, so there are some A, B's and so on written. So what you do is, if you see B, just ignore and move to the right. But if you see A, then you are going to remember here that the number of A's that you saw is 1 modulo 3. But if you see more B's, you just ignore. Again, if you see an A, then you want to remember that the number of A's that you saw is a multiple of is 2 modulo 3. So, and if you see more b's, again you are going to ignore. But now if you see an a, where should q2 go on a?
Except.
No, we still want to count because we have not reached the end. There could be like,
Okay, so it will move left. The tape will move right and will move to the left.
no, we still want to read. Okay, so maybe I'll draw it here. So your input is like very, very long. And what we did so far is we just saw 1A, then Q0 went to Q1. Then if you saw one more A, you went to Q2. Then you see a B, you're just going to stay there, ignore and keep moving right. This is what is happening. Q2 on B just keeps moving right until you see an A. There could be lots of A's ahead. So we want to read all of them. Like, remember the algorithm was that you keep moving all the way to the right. So this is the first step, that you're just going to ignore B's and count the number of A's and keep moving to the right until you see this end marker here. Because at this point, if we are at Q2, we may not have finished reading all the input, right? So we should not make the decision whether to accept or not. It could be that there are only 4 A's.
Yes.
Okay. So, yeah. So yeah, we should move to the right because we want to read the entire input. We want to scan entire thing and before we see that left end marker, which tells us that we have finished reading the input. Also, the other thing is we are keeping a track of count of number of A's. So Q0 tells you that you have seen 0 number of, we're checking multiple of 3, right? So there are only 3 possible remainders you get, either 0, 1 or 2, if you divide any number by 3. So this tells you that number of A's.
Okay, so it will move to Q0.
Exactly. That's right.
Okay.
So this will go to Q0 on reading one more A, and it will still go to right. Now it may happen that somewhere along this cycle we actually saw the end of input, so that we want to take care of. So for example, if you genuinely reach the end of input and now you want to move to the left because that was the algorithm. So we said that you just keep moving left, 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 left until you cannot. When you reach here, you're just going to move to the right, to the left. So if you see this, you're going to move to the left and Q1. Sorry, Q3. Okay, but let's say I'll change the color just so.
If we move from Q0 to Q3, then it will move only once, no?
Yeah, exactly. I have not drawn the whole thing. We will do it
Okay.
together. But from Q1, let's say you see that the input has finished. But what does Q1 say? Q1 says that number of A's that you saw is a multiple of 3 plus 1, because that is what this states. Remember, this says that it is some 3k plus 0. This is basically remainder 0. This is remainder 1. This is remainder 2. So if you reach Q1, that means you have read like number of A's which is not a multiple of 3. Is that fine?
Can you repeat?
Yeah. So if you just simplify the problem, if you just have to design a DFA for checking whether number of A's is multiple of 3, then what we do is you have 3 states. Okay, and each of them remembers the remainder. So this is basically the state that corresponds to having read 3, exactly 3k many ones. But if you reach a state here, then this is not accepting because you have not reached multiple of 3 many A's.
Okay.
Okay, and this is also not accepting. So exactly same thing is happening here. If you are in Q1, then we should not accept, because basically we should directly reject, because we read the entire input. We saw that number of A's was not a multiple of 3.
Yes.
Okay, so that is
So
exactly
it will move on the reject state.
exactly that's right. So we will directly go to the reject state. From here we will continue to remain in the reject state. Whether you see 0 or 1, we are just going to reject. But if same thing happens for Q2 also. If you are at Q2, we have not seen 3k many ones, so we are going to reject it. Same thing. But if you see the left hand marker, the right hand marker from Q0, then there is something else we need to do. We want to check whether number of B's is a multiple of 2. So from this point we're going to, so in terms of tape, what has happened is we were here, we kept moving right, and we saw that
In 2 DFA, can we move both the markers, left and right, or only right?
these markers,
Ah,
these
yes.
are these are like fixed. Okay, that the tape that is given to you is read only, so you can't change any input here.
No,
Okay,
can we move the markers like to which it is pointing?
move as in, I didn't understand. You mean like this
L-
way or this way? Is that
no, no, like the string is AAB.
okay? This is the tape.
Huh,
Sorry, this is AAB, and this is your
huh,
left hand.
huh. So the pointer that reads the string.
Okay, right.
Huh,
That's it.
so
Oh, just a
the
second.
pointer that reads the string, it is the left hand marker. It is a marker, or it is a different thing.
The pointer is different from the marker. So pointer basically can keep moving anywhere. This is like an infinite tape. I mean, this
Huh.
thing will come later on. Okay, so this is an infinite tape, but we are not allowed to change the input. So that's why we have these markers which tell that you are only limited to this space. So um,
So markers are fixed, but the pointer is position of pointer is variable.
exactly, that's right.
Okay.
In fact, later on you will see that this pointer can go beyond the marker also. When that makes sense, when the input is right, I mean when the tape is writable. So if I could write on the tape, so for example I can read B here and I will change it to A. Then I will read this end marker here, I can change that also, let's say, and so on. So if this is writable, then the scope of your pointer is even beyond. But since this is read only, anyway we can't change anything. So I mean, hence the markers basically tell you to stop, and the pointer is variable.
Okay. And in 2 DFA, can we have multiple accept and reject states, or only one?
You can have, but yeah, you can have, but you can also combine them together and just make it one. But yeah,
Okay.
it depends on how you define it. So typically when we give that tuple definition, generally people, instead of writing a set of accept states, they just write one accept state. So it depends on how you define.
Okay.
Okay. So okay. So at Q3 we have basically read the input all the way to the right. Now we want to come back to the left and see the uh, number of B's. Okay, so if you see A's, what we should do is we should just ignore it and keep moving to the left. Okay, and if you see a B, then so just think of this again as just drawing for checking whether number of B's is multiple of 2. So in that case, what you do is you basically ignore the A's. This is for DFA. You ignore the A's. If you see a B, you go to a new state. Again, ignore the A's. If you see a B, you come back to the previous state. And because this is a multiple of 2, you accept on this and reject on this. Right. So exactly same thing we will do here. Okay. So if you see a B, we will go to a new state Q4. If you see A's, we will stay there exactly like we did here. And if we see a B, we will come back.
Okay, so from Q3 it will be accept.
Exactly. From Q3, now we have passed both the checks that number of A's were multiple of 3 as well as number of B's were multiple of 2. So we should accept. And then you stay here no matter what you see. And from Q4 we should reject because it didn't pass the second test. So like you said, I can basically make a new reject state and make a transition there, or just to be consistent with the definition, I can just draw an arrow from here and just go to reject on seeing this we will do on seeing the marker, because only the marker can tell us that we have finished reading the input. Only then we will make the decision. Is this last part okay? This part? The marker thing?
No, can you repeat?
Okay.
Marker made out of.
Yeah. So, okay. So what we did was we first time we came from here, went all the way here, and now this marker told us ki you're finished reading the input. Then we went backward and we were counting the number of bees. Now in between we should not decide here and all, we should not decide whether to accept or not because we have not even finished reading the input. But when you reach this end marker, that tells you you just kept moving to the left. When you reached this marker, it told you you're finished reading the input. Now this is a time to decide whether to accept or not. So that's why, just like here, okay, I'll take this pointer. Yeah, just like here in this case, this thing was exactly same as normal DFA. We were just checking number of A's here and just kept on moving right. Okay, then we made a decision on seeing the the right hand marker only. This thing, and this thing. Only then we decided whether the number of B's was a multiple of 3 or not. Based on that, we decided whether to reject or to continue. Similarly, in this case here, we are counting the number of B's, but when should we decide whether the number of B's is multiple of 2 or not? When we have reached the end of input. And what tells you that you have reached the end of input? These markers here. Okay, so in this case, we are moving to the left. So this is the marker. So if you see the marker and the number of
In the about DFA,
2 DFA.
like 2 DFA. So from Q2 to Q3, it should be right hand marker now, because like if the string ends, then we have to come down now. Come to Q3.
Exactly, yeah.
You have written left end marker, so it will like at the start of the string now.
So okay, so this is the, if I zoom in here, the left hand marker for me is this, which looks like this, and the right hand marker is this. So
Acha. Okay.
actually, I mean, I should have been consistent, but probably at some places I used it interchangeably. But that is what I meant. This is the right hand marker for me in this example. So maybe I'll just write superscript R.
Okay, understood.
Okay. And here this is the left hand marker.
Understood now.
Okay. Okay. So yeah, that's it. Yeah, that's the example. So yeah, the only advantage is that it is sort of very. I mean, what if the algorithm that we did is like very natural thing to try, that like check for one thing, come back, check for other thing, and then if there are multiple checks, you can just, for example, if I were to ask you that L is the set of all x's such that number of zeros is a multiple of 4 and number of ones is a multiple of 3, but number of 0 1 substrings is not or let's say is a multiple of 2. Then how will you modify the, like, just informally, what should the algorithm do for 2 DFA? Okay, so if this was
Like
not
0 1 should be in multiple of 12, na? So that it satisfies both the conditions of zeros also and ones also.
0 1 as in 0 1 as in I mean the substring 0 1. So for example, let's say yeah, let's say this example. In this case, the number of zeros is 3, number of ones is 2, but number of 0 1 as in 0 1 substrings is this one and this one.
Acha, okay.
Okay.
So ma'am, what was the question? Can you repeat again?
So like informally we wrote one algorithm, no, just keep in the previous case we just said that okay, you want to check whether these two conditions happen, we said that you go all the way to the right, check for number of A's, then you come all the way to the left, check for number of B's, and then decide. So I'm just saying informally, if you were to design a 2 DFA for this language, then I mean, then what would the, like, sort of informal algorithm be?
If like it is 0, then move to right. If it is 1, then ignore it.
That's right. Yeah, then you keep
Like
moving.
it will be for since we are counting for 0, so there will be
4 states.
five five sets. Huh?
Uh, for 3, for checking multiple of 3, you just need 3 states. For
Four. Yes, 4 states. Q0, Q1, Q2, Q3. When it is at Q3, if it again accepts a 0, then it will move to Q0.
That's right.
And from Q0, if it is a right hand marker, we will move to left. That
That's
will
right.
to Q4.
That's right. Yeah. Then you do the same thing for checking number of 3s with 3
For
states.
then Q4 will be like when then you will check for ones. Then it will be Q4, Q5. Like it will be one. So there will be 3 states.
That's right.
Q4, Q5, Q6.
That's right. Yeah.
And at Q6, if we encounter a left hand marker, then it will move again back to Q4. First, it
No
was right hand
left hand
marker,
marker.
so it came at the beginning. Then, first it encountered a right hand marker, so we started moving to left for 0 case. Then we came to Q4. Then we check for 1, and at Q6, when it encounters a left hand marker, it again goes back to Q4. Then Q4.
Actually, at that point, we should reject, no? So this is what it looks like. So here you are checking for
Q1, Q2, Q3.
3, and then you go back here on zeros.
0,
And
0.
ones are just here. And everything is right. I mean, is to the right, and so on.
Yes.
So I'm not, okay, I'll just write it anyway. Sorry, this is 0. Yeah, okay. And here if you see your left and the right hand marker, then we go to the left. Then you are
Huh.
seeing Q4. Then there will be three more states. Two more states, yeah. And this is for 1.
Yes.
And zeros will
So
be ignored, yeah.
from Q6 to Q4, again on 1.
Again on 1, that's right. And then if you see right hand, sorry, what do you see now?
Left
You see
hand.
a left hand marker. Then you go to the right.
Huh.
And now you are going to draw an automaton for checking number of 0 1s.
So it will be like Q7. There will be three states again. Q7, then Q8 and Q9. First it will be 0, then move right. 1, move right. Q9, then it will again move to Q7.
Q7 on.
No, wait. It will be Q7, Q8, and Q8. So Q8 to Q7 on entry 1.
Sorry.
Q9 will not exist. Q9 will not exist.
Okay.
From Q8 to Q7 on entry 1.
Um, okay, but this
Then
is
Q7 will go to accept state.
mm, okay. Okay. So there is something I want to discuss about the last part of it. So if you just want to design a DFA for checking number of substring occurrences of 0 1 is, let's say, multiple of 2 or something. Okay. Then how do we do that? You check if you see a 0. If you see a 1, then this is the place where you saw the first occurrence of 0 1. Then
Huh.
yeah, then on the way, if you see lots of ones here, sorry, what I missed. Okay. Yeah, but if you see ones here, you're just going to ignore it because you're looking for 0. Then if you see a 0 here, this tells you that you've seen one occurrence of 0 1. Then yeah, then if you see a 0 here, then you come back here, let's say, and on once you stay here on
But like in the question, it was multiple of 2, no? So it could be 0 also. Like there is no pair of 0 1.
yeah, I mean, I will design it such that even 0 is accepted.
So I have like made on that assumption only. Like at
Uh,
Q7, if there is no pair of 0 1, it will move to accept state. If there exists a pair, it will check and move to accept state. If it is not, then it will go to reject state.
but where is your transition on? Let's say you are at Q8 and you see 0, then where do we go?
Huh, like it is not completed. I have
Oh,
yet to complete.
okay, sorry. Okay, then I'm okay.
If it is at Q8,
Okay, if it is at
huh,
Q8,
then if it encounters a 0,
hmm,
it will go to reject state.
but I mean, it is possible that your string looks like this and you are reading from here. Then you see 0 0. We should, I mean, we should just not count here, but we should still keep moving to the right so that these people get a chance to be counted. I mean,
Okay, so we can make a loop.
we can make a loop. That's okay. Yeah.
Huh.
Okay. And from here, from Q7, if you see a 1,
No idea.
yeah, that's why we need, like, what do you say, two states, I mean, more states to remember whether we have seen even number of 0 1 occurrences or odd number of 0 1 occurrences. So if I just uh,
Okay.
yeah, so if I just simplify this question, instead of multiple of 2, if I just say that um I mean, I mean, I'll just make it 1. So if it's a multiple of 1, that means it's occurring at least 1 is what, okay, is at least 1. Then this thing that you have designed will work, because this is checking whether that happens at least once.
At 1 we can do to reject state, no?
At 1 we can go to reject state.
Because 1 should be multiple of 3, and we have checked in that in the middle one. So more number of ones cannot exist, right?
No, it can. So for example, what was that, multiple of 3? Yeah, and I'll still add 4 zeros. So in this case, number of zeros is 4, that check is passed. Number of ones is 3, that check is passed. Number of 0 ones is just 1.
Or at Q7 you can make a loop. If it is 1, then move right.
If it is 1, then move right. Okay, but in this case, even if you don't see a 0, 1, we will still end up accepting. Or
Because it is multiple of 2, no, so it can be 0 also.
no,
And if it is a 1, it reads it. If it is a 0 1, then it checks it. Like
yeah,
if it encounters a 0, then it would check. If it encounters a 1, then it will pass it. Because we have checked the values of multiple of 3 for ones now. 0 and 1 is checked.
okay.
And we have to check for pair of 0 1. So if it encounters a 1, then it will pass because 0 1 cannot exist. But if it encounters a 0, it will check for 1. Next consecutive entry.
No, I didn't understand what do we mean by 0, 1 cannot exist.
Like there is no pair of 0 1.
Why?
No, like if we take a string for check, in example, like there is 1 0 0 1 1 1 0 0 0.
Okay.
So there exists a no नहीं अच्छा है इसमें भी हाँ so in that there exists one pair of 0 1.
Right.
So if it encounters a 1, then it will move right. If it encounters a 0, then it will check.
Yeah, that's right.
So it is not correct, that loop condition?
So I mean, just want to make sure. So this thing that we have drawn, are you saying this is for the condition that number of 0 ones is at least 1 or multiple of 2?
Multiple of 2.
Okay, in case of multiple of 2, it will get slightly more it will get slightly more complicated, because you want to remember whether you saw even number of 0 ones or odd number of 0 ones. So in this case, if I see 3 occurrences, or let's say just 1 occurrence of 0 1, then also
Okay, so it is valid for condition if it is greater than equal to 1, right? This one.
Even in that, I'm saying, even if you want to check whether it is at least 1, if you just accept from Q7 directly, then Q7 is Q7 is as good as if you hadn't even seen any occurrence of 0 1. So I mean, for example, 1 1 1 0 0 0 0, then your first check of this is passed. Zeros is a multiple of 4, ones is a multiple of 3, but when you come to Q7, it will just stay at Q7, because that is what this one right does, but still it would end up accepting in the end. That's not what we want. So it is still accepting even if there is no occurrence of 0 1. Okay, so only one small thing we need to do is, you just from Q7, if you see a 1, then you are now going to, Q9 tells you, okay, I've seen at least one occurrence of 0 1. Then if you see anything, you're going to accept on seeing the appropriate marker.
It is for 1 or 2 minimum string?
At least 1.
Okay.
The only thing is that previously we were not even remembering that we saw at least 1 0 1. Here Q9, that's why we needed one more state to tell that we saw one occurrence of 0, 1. So
Okay, so from Q7 to accept, it will that transition will go or not?
no, it will not.
Okay.
Yeah. And the remaining are that you just stay there. I mean, the ones that we haven't drawn. If you see one, just stay there, and if you see zeros, yeah, just stay there.
Understood.
Okay. So if you make it multiple of 2, it is slightly more complicated. But easy way would be, if you like, by now you must have observed that whenever we drew this thing, it was just a DFA for checking whether number of zeros is a multiple of 4. We just placed it there and added that right and left transitions appropriately. Then we just made a move here, and the second sort of big automaton is a DFA for checking the number of ones is a multiple of 3, only that there are left transitions everywhere. Then once we are done with that, once the check is satisfied, we are just moving to some new automaton here. And this is exactly the DFA for checking whether number of 0 ones is 1 or not. So yeah, I mean, you can just build the DFAs in small parts and just replace it there. That would also work. And then just move the left and right thing appropriately.
One doubt.
Yeah.
In this, how will we know whether, like, it is only for checking, no, not for making a string? This 2 DFA, it is only for checking, no?
But DFS is also only for checking whether a string is accepted or not.
मतलब like this 2D, this diagram is only meant for checking now and not creating a string.
That's right. That's right.
Okay.
That is the case for every, I mean, DFA, NFA, and all. But the generating sort of thing is coming up this week in grammars. So far we have not, I mean, in the course so far, until now, we haven't seen any example of generating strings. That we will see. Okay.
Okay.
Okay, I mean, that is actually coming up in the coming examples only. Yeah, I think the next example is like that. Yeah. Okay. So, mm, okay, so I think I'll start with the definition. Yeah. So, like you said, that generating strings and so on. So, there are these machines called DFAs with output. Okay. So, yeah, there are two kinds. One is called,
Mealy and More.
right, Mealy and Moore. So, where, I mean, the only thing is, where do you produce the output? So in Moore, you produce the output on the states, and in Mealy, you produce the output on the
Transition.
that's right, on the transitions. So I think then probably, I think we don't need to recall the definition. Then we can just move to the question. So can you try this? Um, if you're given a Moore,
Yes.
yeah.
Input is always equal to output now in More machine.
That's right. In Moore machine, the
6.
right. So for the Moore machine, the length of input is equal to the length of output.
For every input, there will be an output now in both Mealy and More.
Okay, wait. Sorry, just a second. Okay, Moore is the one that goes for states. So, okay, no. Okay, we'll do one example. Okay, so here, I'll take a small one. Let's say this is some um, okay. Okay, so in this case, if I have to, there are three states, and if I have to read a string, let's say 0110. Okay, then what is the states that we are visiting? You start at Q0. If you see a 0, we go to Q0 only. Then you see a 1, we go to Q1. On seeing a 1, we go to Q1. And seeing a 0, we go to Q2. So the number of states that we visited is one more than the length of the string.
So in More machine, it will be input plus one, and in Mealy machine, it will be equal to input.
That's right. Because, yeah, I mean, the number of transitions is equal to the length of the string, but number of states is one more. So in this case, it would be
7.
7. Yeah. Okay, this is sort of very easy question, but since it's there, maybe you can just tell me the answer. So you have a Mealy machine, and you're going to read this input 101010, and what is the output of the Mealy machine? Okay, don't do it that. Okay, we'll just do it together. So from Q1, if you see a 1, you go to Q2 and it says output is 0. Then from Q2, if we see a 0, we go to Q3 and sorry,
0, 1, and then 4 zeros.
0,
Is
1
it correct?
and then 4 zeros. Okay, I haven't done it offline, so I'll do it now. Then you have seen 1. Now you're going to see 1 and you're going to stay there only. Sorry, what? Sorry. You go to Q3 from Q2 and that is 0. Then you are going to read a 0 that takes you to Q2. Then from Q2, if you see a 1, you go to Q3 and say 1. From Q3, if you see a 0, then you go to Q2 and output 0. So the string that I had is 0101010.
From Q2 to Q3, it will be 0, no?
From Q2 to Q3,
At
0.
input 1, output is
Sorry,
0.
sorry. Yeah, so from Q2 to Q3, this is 0. The red ones is the
No,
output.
below 1.
From Q. No, we are going from Q3. Oh, right. Okay. Yeah, thank you. Yeah.
Yes.
Okay, so the answer is 0100 or zeros. Is that
0, 1, and then 4 zeros.
okay? So, yeah. So, okay. Uh, so these two models are sort of equivalent in the sense that if you have a Moore machine, you can convert it into milli and the other way around. The only thing is that we saw earlier that for the same input length, if it's of input length n, then the output of milli machine would be of length n, but that of Moore machine will be of n plus 1. So you're sort of going to trim off the first bit and think of the remaining bits as equivalent, and yeah, and we can show the conversion. So one is very easy, which is that if you're given a Moore machine, then you want to convert a milli machine. That one is sort of easy. So how do we do that?
Transition table.
Yeah, you can do the transition table method, or you can sort of just intuitively also design, which is what I'm planning to do now. So
Okay.
if you are at Q0 and you see a 0, then you go to Q1, and what should be the output? Because if you have visited Q0, then this is what it should be, the 0 then.
Ma'am, can I try this one?
Sure, sure. Yeah.
Done, ma'am.
Okay, so I'll write your answer.
From Q0 to Q1, input at input 0, output will be 0.
Okay,
Uh, Q1 loop 0/0.
okay,
Q1 to Q3 1/1.
okay.
Q3 to Q4 0/1.
That's right. Yeah.
Q4 to Q3
So Q4 to Q3.
1/1. Then Q0 to Q2
Q0 to Q2. Okay,
1/0.
that's right. Yeah.
Loop on Q2 1/0.
Okay,
Q2 to Q4 0/1.
okay.
Q3 to Q2 1/0.
Q3 to Q2 1 slash 0. Yeah, that's right.
0. And Q1 to Q4 0/1.
0 slash 0 slash 1 or 0 slash 0.
0/1.
Mm,
No, sorry, 0/0. Sorry.
okay, yeah, sure. So, yeah. Um, so, did you follow the transition table method or you sort of
No,
directly?
intuitively. Intuitively.
Yeah, that's right. So, yeah, basically you just draw all the transitions as it is initially, and if you have an arrow from A to B and on 0, and let's say B gives you 1, then that's what you're going to write. So if basically look at the tail end at the arrow, and whatever it outputs is
Yes.
what you're going to write on the and it is okay to like drop off this 0. I mean, this 0, it never occurred, right? I mean, because everything was starting from the start state only.
Huh.
So, I mean, just to give a sort of explanation for why is it okay for us is, it's like your machine starts at Q0 and it always outputs 0, and then it's going to output something based on some string of 0, 1 based on the transitions. But 0 is like an implicit thing that is always there. So when you converted it into uh, a Mealy machine, then what it gives you is this string. So if 0x is the output of the Moore machine, then Mealy machine gives you x, and 0 is always there because you are anyway going to start at Q0 and it's anyway going to start with 0 only. So
Okay.
okay, so that's why that equivalence is sort of saying that you trim off the 0 and it is still okay because x is what we care about.
Yes.
Okay, so now we will do the other way around. We're given a Mealy machine, we want to convert it into Moore machine. So here we need a little bit of more work. Um, but yeah, if you want some time, you can try it out.
Yes. No, ma'am, no, not getting this one.
Okay. So, I mean, the transition table method is also like one way of doing it, but like I think we'll do it intuitively here. So you
Okay.
start, okay. So you start at Q1 and um, yeah, and what to write here, it doesn't matter for the first state, because in case of Mealy machine, from going that side, we said that if the Moore machine gives you 0x, then Mealy machine gives you x. So in this case, the Mealy machine is going to give us x. That this is the direction we went in. If the Mealy machine is giving us x, we are going to go to 0x. So without loss of generality, assume that q1 just says 0.
So in Mealy machine there is a loop for input 0, output will be 0. So we should consider it or not?
We should, yeah, we'll take care of that. Okay, so let's look at the zero wala transition. Okay, so this says that on zero you should stay at zero, and it is not violating anything. Q1 is anyway saying giving you output 0 here, so we will just stay. Okay.
Okay.
Okay, now we will look at 1. 1 is also giving 0 output only. So it is also not violating anything, because Q1 is, if you read Q1, it is anyway giving. Okay, sorry. Um, no, this 0 is not the 0 that we should be. Um, I mean, okay, let
With
me draw
0.
it. Yeah, let me draw it. Okay, once. Yeah, this 1, when you see here, okay, the 0 should be here, right? I mean, Q2 should tell you 0.
Uh,
Huh. Okay, so we will draw this state. Okay, and whenever it is consistent with the drawing that we have drawn, we will stay there only. But when it is not, we will make new state. So let's look at this transition. This transition on 0. Okay, it is giving output of 1, which is not what Q2 does. Q2 gives you 0. So what we will do is we will simply make a new state. So I'll do it in red color. If you see a 0, I'm sort of making a new copy of Q2, which gives output 1.
okay.
Okay, and there is a loop here on Q2, right? Here, this is a loop. So if you read any number of zeros, I should just keep giving ones. So I will make that loop here.
Okay.
Now we will now there are two states, like sort of two states that take care of this Q2 and Q2 prime. So we will have to draw for both of them. We'll have to keep branching from both of them. So let's start with Q2 now. So if you are at Q2 and you see a 1, then we go to Q3. And Q3 outputs 0. Is that okay? Because of this thing. If you see a 1, then we want to output 0. So that's why we have a 0. That's why we have a 0.
Yes.
Okay. Then let's look at this transition of Q3 on 0.
From Q2 prime, it will come to Q3 for 1.
From Q2 prime, it will come to, yeah, that is right. And from Q3,
To Q2
from, yeah,
on 0 input.
on 0 input, it should go to Q2. But on 1, there's a different behavior, because it is saying that it should output 1.
Q3 prime.
Yeah, so we make a new state Q3 prime, which outputs 1 on 1. And if you see more ones, we should just stay here. But if you see 0,
It should go to Q2.
that's right. Okay, one second.
understood.
Okay, so I think I'll take up the next question. So okay, so basically, if you have a DFA, there is a transition table associated with it, right? So it tells you from what state on reading what alphabet, where should you go. So you can think of this as a table where you have states written here, Q0 up to Qn, and here you have alphabet, so maybe 0 and 1. So these are the entries that you are given. So this is like a table 1 for some automaton M1, and there is a similar table M2 for some other automaton. So this is the input that is given to you. So input is simply two tables which look like this. There is Q and there is sigma, and you have entries on both the sides. And you want to check whether the language accepted by both machines is same or not. So output yes if language of M1 is equal to language of M2. And also, like, additionally, you know the accept states, okay, like which of these are accepted, that is also something you know. So otherwise you should say no. So
What we have to make?
you want to check whether the language is, so if I give you Q sigma delta F and the start state Q0, then that uniquely defines a machine, right?
But we should have something to make the machine.
It is given to you. This is the table that is given to you. It has all the information. So you have states here, you have sigma here, and these entries tell you the transition table, and additionally I'm telling you what is the final state. And
Not understood this question. Like I have not understood the question itself. What we
okay,
have to do in that?
okay, so if I give you this much information, this tuple information,
Values are there in the tuple.
yeah, that's right.
What are the values? I am asking that.
The delta.
Because no, the values are not available for sigma, for
Okay,
states.
so I'll take one example. Okay, I'll just randomly draw one DFA.
Huh. Okay.
Okay, so this is the DFA. How am I going to represent this? So how the input will be of this form. I will give you Q1, Q2. This is the alphabet
0,
0, 1. Then Q1 on 0 goes to
Q1,
Q1,
Q2, Q1, Q2.
Q1, Q2. Okay, so the input looks like this, and assume that the first state in the I mean, what do you say, like in the table, that is the start state. Okay, so if I just give you the table, what all information I have given you Q, because what is Q? Q is nothing but these states that were written on the row.
Okay.
Okay, and I don't specifically need to tell you sigma also, because this thing is what the sigma is.
Yes.
So Q is done, sigma is done, delta is also done, because what we have drawn is essentially the transition.
Yes.
And start state is also done, because I'm saying without, just assume that the first entry here will be the start state. So Q1, in this case, Q1 is the start state. And I just need to tell you
Final.
what are the final state. So I will just tell you one subset. I'll just write one more row and say that, okay, Q2 is the final state. That's just little bit
Okay.
of more information. So like that, you are given two DFAs, but in this form, you are given like transition table and some information about the final state. Now you want to check whether they accept the same language. That is like some algorithmic question.
So we have to define a DFA, NFA, or minimore, or two DFA.
Okay, this is like the table that is given is for DFA. So you can assume that you are given table for DFA.
सवाल अभी भी नहीं समझा.
Okay, input is clear.
हाँ, like what we have to find.
You
My
want
question is
to
that.
you want to check whether the language is the same or not. But meaning,
So we can take input and output now, like in Milimore, if I want to write. Like if a DFA is given, so we will take the values of DFA as input and check it in Milimore, like output for the second one.
um, but I mean, when do you say that two languages are same? When on every input,
There's the same output.
as in there, I mean, if it is accepted in one, then it is accepted in other, and if it is rejected in one, then it is rejected in other.
Like for zero input, there is zero output. One input, there is one output. If there exists a transition where for zero input, there is one output, then it will go to trap state or reject state. Like,
Right, but I mean, there are infinitely many strings. So how do we check for every string? Because those are infinitely many, then you will just keep running all of them.
no, we can in loop now,
Uh,
can't we?
no, so you are saying that we will check like diagram by diagram. Is that what you're saying? Like, if I give you two diagrams for, I mean, okay, so I'll just take more. Okay, so this is just one thing, and I have not drawn another. But okay, let's say this is M1 and this is M2, and you want to check whether they accept the same languages. And what is your algorithm? If you are speaking, I'm not able to hear you. There was some noise.
No, I'm not. We can directly check the language. Like from this, we can check what is the derived language and then compare.
But language is infinite, no? Um, so I mean, the algorithm will just keep running. There could be infinitely many strings in the language.
There will be a final state, na? Because both are DFA.
Yeah, sorry. So, uh, I mean, when you're talking about languages, you have a set, right?
Huh.
So if your algorithm is checking for equality of languages, then there are infinitely many. But if you're talking about checking the two machines, then are you saying that you are just checking whether like this transition is same as this transition here and transition by transition?
Okay, ma'am, you explain what is the answer.
Okay, so okay, so okay, so basically the idea is that one thing is you can't I mean you can't check I mean I mean you can't just check for every string like you will run for zero and see whether it is accepted. Okay, so one thing is I'm talking about DFAs. Okay, I'm not talking about Mealy machine and Moore machine at the moment.
Okay.
I'm just talking about DFA. So you say that two languages are I mean are equal if and only if X is in L2. That's it. So if I give you two machines, then you can't just check ki, okay, this is my first machine and let's say Q1 goes to 0. I mean stays at 0, then on 1 it goes to Q2, and let's say M2 also does the same thing. M2 on 1 goes here, but then suddenly let's say this makes a transition to some Q3 here, and it goes to it decides to stay here. Just based on that, okay, I think there is some delay in the writing. What I've written on the pad is not. Okay, yeah. Now I think it is reflected. So, yeah. So I'm saying that you can't transition by transition. You cannot check in the table. So you have some entries like this in the table Q1, Q2, 0, 1. You can't say ki, okay, if all the entries here match, this is the table to some Q3 and so on. You can't say that if all the entries here match, uh, then the languages are same. Is that okay?
So what is the final answer for this?
No, I mean, I'm just saying that. Are you okay with this part of the
Uh-huh.
argument? Yeah. Why is that? I mean, why is that not right to say that? Just take the transitions.
Because in different transition also, we can get the same output.
Right. So, like, there could be one. I mean, there could be different machines for
Like
the same language.
transitions can be different, but output may be same.
Exactly, like we saw in the case of minimum state automaton. So there, the number of
Yes.
states itself was different, but still the language was same. So this is not enough. Also, what we cannot do is, because it says that for every x, if it is in L1, then it has to be in L2 and the other way around. So obvious thing would be that you just check for every sigma star. So you check for 0, run it on M1, check if it is accepted, do the same for M2 and see whether that matches. Then you check 1, then you check 0, 0, 0, 1 and keep running and keep checking whether they are same. But that will go on till infinity, because there are infinitely many strings that we need to check. So this is also not good enough for us.
Okay.
Okay, so I'll just write a few lines. Okay, so approach 1 was that you check the table. Okay, but this won't work because counter example is question 1 that we saw today, which is minimum state automated. And the approach 2 is that you check for all x in sigma star. Uh, if M1 accepts x, then M2 accepts x. This is also not enough because these are infinitely many strings. We want to terminate at some point. We want to conclude whether it is equal or not. So what we will do is, okay, so
Basically, we cannot predict. Answer would be that now. We
no, no,
cannot predict.
no, no, we can give an algorithm. That's what we will see now. Okay,
Okay.
so if I give you some machine name, okay, some DFA like this, okay, how do you make language for how do you make machine for the complement of that language? From this M, how do we get to M prime such that the language accepted is exactly the opposite?
Reverse the inputs.
Um, or swap the final and non-final states, because
Yes.
reverse, yeah. So all the final states here become non-final here. So here it would look like this. Basically, just swap the final and non-final states. Okay. So what we will do is, you are given two tables, one for M1 and one for M2. So for M2's table, we will the table is the same, only that there are some final states here, there are some final states here. Only that we will change this F2. We are only changing the final states, and that is everything except F2. Okay, so I'll call this M3. So language of M3 is nothing but language of M2's complement. This much is okay. Okay, that is the only thing we did. We just changed the F2. Now, if M1
Intersection should be null of L1 and L3.
exactly. So that's the algorithm. So if L of M1 intersection L of M3 is equal to empty, then that means that, okay, in fact it is if and only if. So that means that L of M1 is equal to L of M2.
Thus, that's it. The answer is this much only.
Yeah, that's it. And how do we do this? We already saw that cross product thing, no? Uh,
Uh,
if you get two machines, how to get the intersection is just that you do that q p comma q sort of tuple wala cross product thing. Then you get some other m prime. And how do you check whether it is empty? Just that the final state will never be reachable.
yes.
That's it. That's the algorithm.
Okay.
Okay, so there's one more question, but I think I'll take it up later. I'll just show you if you want to think about it offline. But I think, yeah, that's all for now. Okay, so I'll stop the recording, but if you have questions, I'll stay for 5 minutes.